The topic of this presentation is fast quantum gate design with deep reinforced learning using real-time feedback on readout signals, which is an extensive title, but we're going to go through every part of it, and I'll take you through it. This is my master's research, which I just completed this past summer at the University of Victoria in Canada, under the supervision of Rogério de Souza. And I am continuing in this vein in my PhD, so I'm hoping to take this algorithm even further. So before we get even into reinforcement learning or gate design, what is quantum information and what are we even trying to work with here? So in a classical computer, when we think about information, we just think about bits, which are 0 or 1. But quantum information can take on some superposition of 0 and 1, which is a buzzword in quantum, I would say. And essentially, it means that if you were to measure your quantum system or observe it, with some probability, you would get 0, and with some probability, you would get 1. So that's this fundamental unit of information when we're dealing with quantum computers and trying to process information quantumly. It's this superposition with 0 and 1, where alpha and beta tell you how likely it is to measure 0 or how likely it is to measure 1. Now, it's all well and good to have quantum information, but if we want to actually do something with it, manipulate that information to perform computations, we need to do operations, and we call those operations gates in quantum computing. So a gate does something to this superposition of 0 and 1. For example, we could talk about what's called an X gate, a NOT gate, which we also have in classical computing, and it just changes this 0 to a 1 and this 1 to a 0. There are other gates listed here. If you're in the quantum computing world, you'll recognize them, maybe the Y gate and the Z gate. And then you can also do operations on more than one qubit, of course. When we have multiple bits, we can combine them together. Same thing with multiple qubits. We can do operations on more than one. For example, let's say I have this qubit again, which has this superposition of 0 and 1. And then I have a second qubit. And when that second qubit is off in the 0 state, I don't do anything to the first qubit. But if that second qubit is on in the 1 state, then I do that NOT gate, the X gate, changing this 0 into 1 and changing this 1 into a 0. So that would be an operation on 2 qubits where there's some control qubit, qubit 2, and based on the state of that control qubit, I do something to my initial qubit. And the idea, a sort of motivation, is that we still don't have perfect operations to do these gates. In theory, it's super nice to just change it to 1 and I change it to 0, but in practice, complicated electronic process. In the broad sort of scale of quantum computing, right now we're in, you might have heard the NISQ era, this acronym about noisy intermediate scale quantum devices, which are sort of small devices with, say, 200 of these units of fundamental information, these qubits. And when we encounter problems, right now we just sort of try and mitigate them, fix them after the fact with maybe error mitigation protocols is what it's called. And that's something I definitely encourage you to look up. The super cool work that I did at Keysight was all about error mitigation. But we're hoping to move into a new era of quantum computing with tens of thousands of qubits where we can actually do useful computations and have advantage over classical computers. In order to perform these computations at a large scale, we need to control quantum systems subject to a lot of hardware noise and fabrication variability. And so that's sort of the motivation behind trying to make better quantum operations so that we can have large-scale quantum computers, which we hope will eventually outperform classical ones in applications such as optimizations. Of course, you might have heard about cryptography and how important that's going to be, and then some simulations of quantum chemistry, for example. These are the kind of application areas that we might look for quantum advantage. So I study a specific type of quantum bit. This is the way that we physically represent the quantum information. It's in what's called a transmon qubit or a superconducting qubit. This is the kind that I work on. There are other kinds of qubits out there. But superconducting qubits are an electrical circuit like the ones shown here. And if we talk about a regular electrical circuit, which just has a capacitor and an inductor, we can use some theories of circuit theories just to look at what the energy in that system looks like. And it turns out that we can quantize it, or we're doing quantum here. And so we can talk about specific levels of energy, a ground state where there's not much energy in the system, and then excited states above that where we have more and more energy in the system. But let's say I want to do a computation where I'm interested in a qubit. That's, remember what we said, only had two options, 0 or 1. So I want to isolate to these energy levels down here. Well, that's hard to do when these energy levels all look the same. So I have to make the spacing different so that I can do my computations only in the 0, 1 area where I want to have a qubit at two different possible states and not those higher energy states. In order to do that, I introduce a nonlinear circuit element. So it's replacing the inductor with a different kind of circuit element called a Josephson junction. And a cartoon diagram here on the left shows what a Josephson junction might look like. It's two pieces of superconducting metal separated by an insulator. And the equations under it, if you're interested, show how the current and voltage depend on each other and depend on this superconducting phase between the two islands of superconducting metal. So that's the sort of engineering side of how you might build such a qubit that I am then going to try to control. So remember, this qubit is built of a capacitor and a Josephson junction, and I can use another capacitor to couple that to a voltage source. And if I send a wave voltage down this line here, then I'm going to affect the voltage and current in the circuit, and in that way, I control the state of my quantum bit. For those interested, and those who know a bit more quantum mechanics, the Hamiltonian for that system, which is a way of defining the energy levels, sort of looks like this, where A and A dagger are the creation and annihilation operators. That means if you put those on a state, the creation operator gives it more energy, the annihilation operator gives it less energy. This voltage drive is what I talked about. It's something you would design and send on purpose. And then these sort of coefficients determine, the capacitance, and there's a E factor in there. Those are just some scaling factors. And I'm going to hide those complicated scaling factors inside this control function that I'm just going to call C of T. So it's determined by the voltage drive they sent in. And I'm going to hide all the control factor, prefactors inside of that. So the idea is, how do I make this C of T or this VD of T a good shape so that I do the operation that I want to do on my quantum bit? I will skip this math slide. I think it's maybe, well, no, we'll go through it. So like I showed you, there's the drive Hamiltonian with creation and annihilation operators, which means essentially, if you just look at this mathematically, this makes the state have more energy, this makes it have less energy. And there's a nice specific format that I might want to put my control drive into. So focusing here where I have this cos and sine, you might notice that I've split my control into two pieces, which I call X and Y. And we're going to see why that's useful just below here. If I go through what's called the rotating wave operation, again, for those who are sort of more following along with the quantum mechanics here, that means I'm going into a frame of reference that rotates at the same frequency as my qubit. But don't worry if you don't follow that. It's not the important part. The important part is I've chosen a specific format for my control function, where if I do this approximation, it turns out that the X drive does X gates and the Y drive does Y gates. That's what I want you to get out of this slide if you're not really following the specific quantum mechanics. So here's what the sort of energy of my system looks like in time. I've got just some Z portion that I don't control, and then I've got a control envelope that does X operations and a control envelope that does Y operations. So if I think of you might have heard of the block sphere. If I think of my qubit as something in 3D where there's a 0 and a 1 state, which are the two possible states in my qubit, and then they can be in any superposition of 0 and 1. Then an X operation rotates about the X-axis, a Y operation rotates about the Y-axis, and then the Z operation rotates about the Z-axis. So that's the sort of mathematical background and setup for what I'm trying to do. Now let's try and look at what I do, how I would make a NOT gate using these operations. First, I don't want any Z parts. So I'm going to make the frequency of the voltage that I send in equal to the frequency of the qubit that's rotating naturally. So that part is canceled out. I also want this to rotate around the Bloch sphere, the sphere, by exactly halfway around. So pi radians. So I'm going to make the rotation amount pi, and then I don't want any Y rotation for this X gate. So the important thing is that I need my drive on the X to equal pi when I integrate over time as I do the operation. In the end, I want to rotate halfway around the sphere that represents the state of the qubit. So what have we learned so far? It's that we've got quantum information that can be represented as a superposition of a 0 state and a 1 state. And those states, if you want to picture them geometrically, can live on a sphere anywhere on the surface of that sphere with a radius 1. And if I want to do operations, what I'm doing is rotating that state around the sphere. And in this talk, I'm specifically focusing on X operations. So I want to drive just the X direction. And I have a control envelope to do that, which I send in on a voltage line. And however much that control integrates to is how far I rotate. Are there any questions before I get into a bit more about the algorithm? All right. In that case, either you followed the physics or you followed the hopefully more simplified explanation. Let's skip to two-level gates. One more important thing is, okay, great, I've done a gate. I've done some operation on my qubit, but how do I know what the result of that computation even is? Because of course I want to get something out of the algorithm at the end. So we use, again, another capacitor, and this time we couple the qubit instead of to a voltage to some sort of resonator, which is just another circuit component. And it turns out that if I send a microwave into the resonator, when I get it back out, the frequency that it comes out at depends on the state of my qubit. Now I can talk about, so that's what I say in the Hamiltonian. If you're interested in reading those, you can see here that that there's a qubit state dependent shift in the resonator frequency. So when I measure that signal out from the resonator, it has two components, which are normally in literature called in phase and quadrature. So I get out this signal and it has two components, in phase and quadrature. If I plot those components against each other, depending on where my data ends up on the plot, I can say what state my qubit was in. Now, at the start, I said we want to be in the 0 state or the 1 state because that's how we define a qubit, and that's where we want our computations to be. But it turns out that sometimes by accident, we go into higher energy level states. So I've also shown the 2 state in this measurement diagram. It's possible to measure higher energies. So again, the idea is based on this, I can read out the state of my qubit by probing a resonator. And the way I actually quantify that state is by plotting the two components of the readout signal against each other and seeing where on the plot that data lands. And these plots can look different for every different qubit and processor that you're working with. So you do have to sort of characterize them beforehand. So I've now described a simple model where I've got a regular circuit with a Josephson junction then replacing the usual inductor. It's coupled to a drive line for control, and it's also coupled to a resonator for measurement. And that measurement shows up on this IQ plot where I try and figure out what state the qubit was in. In reality, we've got huge quantum devices with engineering constraints like maximum amplitude on the drive that you can send in, and quite complicated physical models and noise processes. So I showed you some nice Hamiltonians, some nice equations for how you could define the system. In reality, it's much more complicated, and it's very difficult to build, or I would say impossible, to build a perfect model of your superconducting quantum processor. And that, of course, leads to errors in the operations. Like I mentioned, one of the errors that we don't want to happen is going out of what I'll call the computational subspace down here with 0 and 1 and accidentally leaking into higher energy levels. IBM offers access to their quantum devices. So I ran some gates on their actual hardware. And this is an example of what the output looks like after that X gate. So I tried to go from the state 0 to the state 1 by applying an X gate. And there was some leakage into higher energy levels, which is not what we wanted. We want all of it to be in the 1 state. And there was also some leftover populations in the 0 state. So this is after I tried the gate 1,000 times and saw the result 1,000 different times. Sometimes there were mistakes and it leaked into higher energy levels, and sometimes there were mistakes and it went back down into the 0 state or never left the 0 state. And we want to get higher quality gates, so we want to reduce these errors in order to be able to build larger scale quantum processors and do more complicated algorithms on them. There are some, of course, control strategies already for how to do these gates better. Usually right now they're analytic, so someone just comes up with an equation, or they're based on numerical simulations, which both require precise physical and noise models of the hardware. You want to know what equations you're dealing with. If you want to make a simulation, of course, you need a model. And if you want to do something analytic, you need a mathematical equation to tell you about the behavior of your system. And as I mentioned, those are both challenging to get at these precise physical and noise models. For example, IBM uses a relatively simple analytic formula called drag, derivative removal by adiabatic gate. And the idea is just this simple Gaussian shape. So this is what C of T looks like. And just like my signal coming out of the resonator had 2 components, my voltage signal going in has 2 components. And it turns out that if you take the derivative of that Gaussian and put it on the second component, this also reduces the leakage. So this was one suggestion for an analytic solution. But the noisy gate that I showed you was already using this solution. So we need to go even further and do even better. But I will tell you why I introduced this one later. It's a useful starting point, I would say. So my solution to this is an algorithm called deep reinforcement learning. It's well known in the literature. It's been used before for quantum control of quantum systems. And I would say the basic idea is you have what we call an agent. So this is just code on your classical computer. It's an agent, and it's going to make decisions about what you should do next for your controls. How does it make those decisions? It has to observe what happens to the quantum system and calculate some sort of reward or punishment for how good the action it took was. So it's a cyclic algorithm where your agent decides on an action, it observes the result of that action, and then it takes into account how good or bad that action was. And the nice thing is you don't need a model because it interacts directly with your quantum system by observing it and then taking new actions. So we don't have to try and quantify all these errors and complicated connections between qubits on a big quantum processor. And some recent advances in control hardware have also opened up the possibility of doing this very quickly, what we could call in real time, as in there's no sort of long delay between when you observe the state and you decide on your new action. So it's also a fast way of designing controls, which is important if we have to recalibrate often. Say the noise in your quantum processor changes over time, You don't want some long, complicated algorithm for how you're going to update your gates to keep up with those changing parameters. My specific algorithm, this is the sort of the cycle that I take. I've got some sort of agent, and I'm trying to build a control pulse to do this X rotation that I talked about. In order to do that, my agent is going to propose the amplitudes for a little piece of the control pulse. And then it's going to run that pulse on IBM's hardware in this case. And then we're going to reward how good the result of that pulse was. Ideally, right, we want to be on this IQ plot in the one state, like I showed before. And also, I'm going to specifically focus on penalizing that leakage into the higher energy state. As I showed at the very beginning, the way that we're going to be able to use these quantum processors in the future is by algorithms called error correction. But these algorithms aren't very good at dealing with leakage. In fact, they can really mess them up. So yes, decoherence into the one state, into the zero state is also bad, but this leakage is particularly detrimental to error correction algorithms, which we need for large-scale quantum processors. So I'm going to focus on reducing leakage at the same time as trying to get a nice gate that gets me into the one state. After I run this pulse, then I propose the next segment in the control. And the way that this pulse is built up sequentially means it can be as short or as long as it takes to get the gate right. And that means I haven't started by telling it some length that the gate needs to be. I'm letting it build up as it goes. And so it can make faster gates, because if I just said, oh, I need a gate that's 64 nanoseconds, then I would have to try and make that right. But instead, it can build a gate quickly, segment by segment. And if it gets to the one state faster than 64 nanoseconds, there you go. You've got a faster gate. As I mentioned, gate. There's reduced measurement error in my scheme. Many reinforcement learning schemes so far, they instead of taking the location on this IQ plot, they go one step further and they actually classify that state. So they say, oh, it was exactly 0, or it was exactly 1, or it was exactly 2. I just say, oh, it was closer to 0, or it was closer to 1, or it was closer to 2, which means I don't lose information by trying to classify my measurement precisely. There are 2 agents in my architecture, one to deal with the regular pulse and one to try and reduce leakage. And as I mentioned, we also now have the option for real-time feedback, so I can build my pulses quickly. Now that's nice, but it's a bit challenging to just start from scratch and train your agent to build a gate. So I also pre-train my agent. And that's why I introduced the drag pulse, which we know is pretty good, even though it's not perfect. So I train my reinforcement learning agent first to favor this Gaussian shape that I know is advantageous. And then I'm going to go from there and fix it, shall we say, as time goes on. So here's an example of my agent building an X gate. The left shows the pulse, the right shows the state as time goes on. As you can see, it gets to 1 sort of even before the end of building the gate. I'll play it one more time. This is the state. It's going closer and closer to 1 as time goes on. And then it kind of gets there. And it's even there for a little bit. So maybe my gate could be even faster than this. But this is an example of the pulse shape that comes out. You can see it kind of still looks a little bit like that Gaussian that we saw before that was close to optimal, but it's got some significant differences. Now, I did this for X gates and also a square root of X gate, which means it tries to just go halfway instead of all the way around the equator. And I compared them to this default drag gate that I said IBM uses. And I compared them in terms of 2 metrics. One of these metrics is called fidelity. If you have some target state that you want to get to and you have your actual state, fidelity is the overlap between those 2. And they also measured just the leakage population, what percent of the population was out of the computational subspace where I really don't want it to be. And here we can just see, let me compare the gates that are the same length, they're the same duration, my optimized gate and the drag gate. My optimized gates have higher fidelity and lower leakage than those default gates on IBM. So the agent was able to find better gates. And what's maybe more interesting is that I can make gates that are 2 times faster and have comparable performance in terms of fidelity and leakage. So the fidelity in this case is ever so slightly lower, but the leakage for the X gate is still better. And this gate is 2 times faster than the initial. That means my algorithms would be twice as quick to run. And one of the great things that we're already looking for in quantum advantage is to perform faster calculations than classical computers. And another important thing with having faster gates, if you know a little bit more about how quantum systems work, it turns out if you put more energy into them and excite them, that energy finds ways to escape. And so you sort of lose that nice excited state over time. So if you want to get your operations done before that happens, so it's nice to have faster operations that preserve your quantum state for longer. So here are what those pulses look like as an example. It's the 2 times faster one, the 1.3 times faster, and the same length as the drag, which is the default in the bottom right. And sort of same idea for the square root of x. But these ones look a little more complicated. And then I also wanted to see how long those gates would last, because then, as I said, the noise in those processors kind of changes over time. So without retraining the agent, I looked at those gates 1 month later, and my gate is still a little bit better or equivalent, I would say, performance to the default gate, which is shown on the right here. So my gates are also as robust, I would say, as the default. So what have I shown overall? That existing controls for quantum computers are suboptimal, usually because they're built using simplified models. Reinforcement learning is model-free, so it's a good approach for designing controls for quantum systems. My proof of concept on IBM devices shows better gates in terms of fidelity and leakage. And it also shows gates that can be 2 times faster than the default. But in the future, I would love to increase the smoothness of these pulses by making them using more segments, making them a bit more complicated. Those segments were kind of choppy. Run experiments for 2-qubit gates. Find some better measures for the success of the gates. So fidelity and leakage are fine, but there's a sort of more popular way of measuring the success of your gate called randomized benchmarking that takes into account the other gates that you might run on your processor, and generalize to other types of qubits and devices and see how the gates and agent work on other devices. So if I train the agent on, say, one quantum processor, and then I use it to design gates on another quantum processor, does that carry over at all? Lots of questions for what else you can do with this. Thank you so much for listening, and I'm super happy to take questions.
Thank you, Emily, for your presentation. Please let us know if you have any questions. Let's see. Okay. I have a question for you, Emily. What are the hyperparameters of your reinforcement learning algorithm, and how do they affect the success of the algorithm?
Absolutely. So the hyperparameters are extensive. I would say the biggest ones are, well, let me go back to just showing one of the pulses maybe. So I have to pick a set of amplitudes that I allow for each segment. It's not a continuum. And so I could get more complicated pulses if I allowed more fine-grained amplitudes. However, it would take the agent longer to learn that landscape because the landscape would be bigger. So that's one trade-off. Another one is just the reward function. So I think I put it in the appendix here, which maybe won't mean much, but essentially, remember I was showing those plots with the I component and the Q component. So this is the distance between the target location I want it to be on the plot and the actual location on the plot. And then some sigma parameter, which says what was the distribution of that cloud when I figured out the target. That's an example. This is the reward function I use, but there are lots of other possibilities for what kind of reward you could use to tell your agent whether your pulse was good or not. That's another big hyperparameter. And it's great that you asked that because actually today I was working on defining what my next steps are for how I would like to test different hyperparameter configurations and figure out the best one. Because we certainly didn't have time to do that during my master's project. And it's well documented in the literature that the hyperparameters you pick have a huge effect on the success of your algorithm. One other thing I'll show here is this shows the training iterations, and this shows how many of the gates that came out of after that number of iterations had a fidelity of better than 90%. And as you can see, it's still increasing at the max number of iterations that I use. So my agent hasn't converged all the way. With the access to hardware that I had, I couldn't do more training iterations than that. But this is another hyperparameter that I would love to extend and see if I can, in general, change my hyperparameters and get a full convergence.
Very good. Thank you so much. We have a question. What have been the greatest challenge when trying to reach one state in your testing?
So the greatest challenge I would say is the trade-off between making a faster gate and getting more leakage. Because in order to get a faster gate, you try and ramp up the amplitude of your pulse usually more quickly. So you need more power, more amplitude because it's a shorter time. You still need the same area of pi under your pulse. So when you put more energy in steeply, it leads to more leakage out of the computational subspace. There's a real trade-off there between trying to make a fast gate and trying to make a gate that has less leakage. And that's why I used, in the end, 2 different agents, one to decide on the first component of the signal, and one to decide on the second component of the signal, where the second component was just meant to stop leakage from happening.
Very good. Thank you. Let's jump to Atiyya's presentation. Thank you very much, Emily.
Yes, let me just figure out how to end my screen share. Zoom, show me the meeting controls. There we go.
Great. Thank you.
Okay. Hi, everyone. My name is Atiyya Davis, and today my presentation will be on characterizing entangled source performance. Okay, so a little bit about me. I am currently a third-year PhD student, and I attend the University of Illinois, Chicago, and am completing my research at the Army Research Lab in Adelphi, Maryland. So today we're going to first talk a little bit about quantum technology and what is quantum technology. Quantum technology is a class of technology that operates using basic principles of quantum mechanics. Some emerging technology you can see here that you may be familiar with, such as quantum computers, sensors, communication, and simulations, all which operate on the fundamental principles of quantum mechanics. So quantum technology offers performance benefits compared to its classical counterpart, such as secure communication, enhanced computing, and many other applications. And this all fuels research interests in areas such as quantum networking. So quantum networking essentially connects systems and transmits data using the quantum phenomena, where entangled photons travel through an optical fiber, for example, which helps maintain the quantum states and the qubits carrying the data. So researchers are currently working towards true quantum networks where we can use secure quantum channels to transmit data over large streams, such as like a college campus, for example, or a data center, or a metro area network, or WAN. But in order to get these practical applications of quantum networks, we must be able to get these quantum networks to store, manipulate, distribute, and generate quantum states. So in order to generate quantum states, we use an entangled photon source, or EPS for short. And an EPS is inherently fiber-based, which provides low-loss coupling to exist in long-distance fiber networks. Since the EPS is inherently fiber-based, they can be easily integrated into pre-existing fiber networks. So that's what makes them ideal for this use. However, when using an EPS, we would hope that the EPS would be able to generate noiseless entangled photons. However, that is not the case. The entangled photon source is affected by multiple sources of noise created by nonlinear optical effects known as Raman scattering and self-phase modulation. So basically in this presentation, I'll be showing you how we characterize the EPS and the photons output by the source under different conditions, along with different methods used in the characterization process of the EPS. So when characterizing the source, we use quantum state tomography to determine the quantum state of polarization of the entangled photon source. Quantum state tomography is the process of characterizing a state in a quantum system through a series of measurements to determine the density matrix of the system. And when dealing with high dimensional systems that are there are inherent trade-offs with various approaches to quantum state tomography. So each method has its own trade-offs and challenges and difficulties. And some of these different approaches include linear inversion, maximum likelihood estimation, and Bayesian inference. And when characterizing the EPS, we use in the lab I work in, we use maximum likelihood estimation method, but in other instances, the Bayesian inference method is known as the more efficient method. So in this presentation, I will demonstrate the use of both the Bayesian inference method and the maximum likelihood estimation method in separate cases. However, like I said, each method has its trade-offs when it comes to quantum state tomography. These trade-offs include things such as long computation times and accuracy, and just the general assumptions that we make about the system. So the different applications of quantum state tomography I'll talk about very shortly. But first, let's take a little look at our experimental setup. So figure A right here shows the experimental setup of the EPS. So the system consists of the EPS, the entangled photon source, 2 polarization analyzers, and a correlated photon detection system. And all of this is connected via optical fiber. So the EPS itself is a self-contained source of entangled photons. The polarization analyzers, or PAs, contain wave plates and a polarizer to perform measurements. And the detectors include 2 single photon detectors to perform coincidence measurements. The EPS works by generating signal and idler photons via a process known as 4-wave mixing in the zero dispersion region of the optical fibers. And it does this by pumping the dispersion shifted fiber with a 50 megahertz pump pulse laser. And this dispersion shifted fiber, or DSF, is arranged in a stagnant loop, which you can see here, with the polarizing beam splitter at the end. And this is used to entangle the signal idler photons in polarization, and this creates a Bell state. So when four-wave mixing takes place, it generates the signal and idler photons, and then the EPS demultiplexes them into channels. So now we have the signal channels and the idler channels, and I'll get more into the channels later. And each of the channels are at different wavelengths. So in order to characterize the EPS, we use methods like quantum state tomography, which I mentioned. We look at the concurrence of the quantum state, and we measure the coincidence to accidental ratio, which is also known as CAR, which I'll get into more a little bit later. But as you can see here, I have a list of the channel pairs, and each of these channel pairs are located at different wavelengths. And let's just take channel 2834, for example. So the correlated channel pair 2834 is used to detect photons on the same four-wave mixing pair. So in order to produce a maximally entangled state, the pump must be set to 45 degrees at the input of the stagnant loop polarizing beam splitter. So the internal polarization controller is automatically adjusted until the power at the output of the loop is maximized. So when setting the detectors, for example, we have to set a relative delay so that we can synchronize the arrival of the photons. This ensures that both photons from the same pair are arriving at the same time. This is very important. This also allows us to measure the coincidence between channels 1 and 2 at the same time, which I'll touch on in more detail a little bit later. And you may be wondering why we have to set the delay. For our system specifically, channel 2 is electronically delayed relative to channel 1. Therefore, we have to manually delay channel 1 in our software so it can detect the photon pair at the same time. If you can't detect the photon the same pair, then no results. So as stated previously, the EPS generates entangled photon pairs via four-wave mixing. And just a little description about four-wave mixing for anyone who isn't familiar. It's basically what is a third order nonlinear optical process where four waves or photons interact, and as a result, new waves with the sum of they interact, and as a result, new waves with the sum and difference frequency are generated. So basically, the pump photons are entangled, and when they're placed in the DSF, in the stagnant loop PBS, the four-wave mixing is not the only way to produce photons in the system. The photons are also generated via cell phase modulation and Raman scattering. So the four-wave mixing photons are the entangled photons, and the cell phase modulation and the Raman scattering photons are the noise photons produced by the source. So a little bit about cell phase modulation. Cell phase modulation is also a nonlinear optical process, and it's caused by the spectral broadening of the pump laser. And so it outputs additional noise photons at the output. So we predict that channel pair 2933 would experience the most cell phase modulation because it is the innermost channel, and it has small detuning from the pump since it's closer to the pump, which is located at channel 31. And Raman scattering is a result of a nonlinear interaction of the pump photons. And Raman scattering increases as detuning from the pump laser increases. Therefore, we predict that channel 2636 is expected to have the greatest amount of Raman scattered photons. However, in the recent literature, cooling the dispersion shifted fiber has been documented to reduce the amount of Raman scattered photons. So you will see that we end up doing that in our experiment as well. So due to the presence of the noise photons in the system, one of our objectives is to determine optimal operating parameters to minimize the effects of the Raman scattering photons and the self-phase modulation photons. So we can do this by characterizing the EPS as a function of power and temperature. But before we get into the characterization of the EPS, I want to go back to the methods of quantum state tomography that I mentioned earlier. So in characterizing the EPS, we use quantum state tomography. Like I said before, quantum state tomography has many methods, each with its own trade-offs. And later I'll discuss the method of maximum likelihood estimation. But right now I want to shift gears and look at the Bayesian inference method as a means of quantum state tomography. The Bayesian method is looked at as the better alternative as compared to the maximum likelihood estimation method. And you may be asking, why am I using two different methods as if one is thought to be superior? Well, as you know, every method has its pros and cons, and each new method is created to improve upon the challenges of the previous method. So Bayesian is said to have reliable estimates under certain measurement conditions. It quantifies the natural uncertainties and has a minimal mean squared error, But the challenges of Bayesian include long computation times and issues with incorporating prior knowledge. So in order to mitigate these problems and see the effectiveness of the Bayesian inference method, we chose to use the machine learning prior in order to customize the prior distribution for this Bayesian state estimation. So prior distribution is just an initial set of beliefs regarding the states that might describe your system. So we used here in this example, we use the results to find experimental results to find out if the machine learning prior reduces the net coverage times and if it provides a way to include information directly into the prior distribution. So figure A and B show, again, the same setup of the EPS and the density matrix that I showed before. The EPS setup for this experiment is pretty much the same, and then the density matrix is made up from the quantum state tomography. So the machine learning prior uses a pre-trained neural network to define a custom prior that automatically adapts to the data. And this is one of the reasons why I guess it's the more superior method, because it's able to adapt to the data. And this is what sets it apart from the maximum likelihood estimation. So to demonstrate the efficiency of the machine learning or ML prior, we apply it to the states generated by the EPS. So with using the EPS, we take the dispersion shifted fiber, DSF, and we cooled it to negative 86 degrees Celsius to reduce the amount of Raman scattered photons. And we took 1,000 tomography measurements, and I think the runtime was around 4 hours for this to run all the tomography measurements. And the density matrix was calculated using the ML prior. So figure A shows the fidelity of the Bayesian state reconstruction as a function of total computation time. The blue shows the reconstruction of the Buras prior. The red shows the ML prior, sorry. Y'all see that. So what can we tell from this plot? So here it tells us that the machine learning prior significantly outperforms the standard Buras prior. So the red outperforms the Buras prior for short time scales, but the Buras prior reaches a higher peak fidelity with longer computation times. And you may be asking why, since we suspected machine learning to outperform the standard, which is the Buras prior in this case. And we found out this is due to the fact that the machine learning prior is being overly biased towards the experimental ground truth. So we add in the green curve, and which is added in at a reduced bias, which ultimately outperforms the Buras prior at the long computation times, but it reduces the initial reconstruction fidelity compared to the red curve. So, okay. Figure B gives you a better idea of the advantages of the machine learning prior. It shows the probability density function of purity for the fixed BRS prior, which is in blue. Can't see my mouse, okay. Which is in blue. The ML prior in red and green, and the density matrices from the experimental data with the maximum likelihood estimation in black. So we see very little overlap with the fixed BRS prior compared to the ML prior, which successfully adapts based on rapid reconstruction. But the lower bias green covers the experimental distribution more uniformly than the higher bias red curve, which may contribute to the fact of its higher fidelity in the previous figure, figure A. So now that we've looked at one method for quantum state tomography, let's go back to the other method I mentioned, maximum likelihood estimation, to characterize the EPS. As stated before, all components are connected via single mode optical fiber. So for this experiment, we're characterizing the EPS as a function of temperature and power. Therefore, we adjust the temperature of the freezer, which contains the dispersion shifted fiber, and we range that from -86 degrees Celsius, which is our lowest temperature setting for our lab freezer, to 20 degrees Celsius. And then we also adjust the light pump power from 3100 to 3800. We then measure the coincident detections of both photons in 36 different joint polarization bases. This is like just specific for our experiment. You can pick whatever combination that you would like, but this is what we chose to do. And the set number of gates that we used it so that the max number of coincidences at any joint polarization pair is greater than 1,000. And the maximum likelihood estimation is performed on each tomography run. So the tomography is performed on all 4 channel pairs at each power setting at the various temperatures. And so the average concurrence for each of the 10 runs per setting were calculated. So just a refresher, but concurrence is an entanglement metric. So 0 represents a separable state, 1 represents a maximally entangled state. The concurrence is shown as a function of attenuation for each channel pair at 20 degrees Celsius for A and -86 degrees Celsius for B. And you can see the decrease in concurrence due to the spectral broadening of the pump. And this is because of the noise photons I mentioned earlier, but more specifically due to self-phase modulation. The decrease in the concurrence is the greatest for the innermost channel, which is in like this purple color, 2933, because as I mentioned earlier, as we predicted, it has the smallest detuning from the pump. So it's getting the most leakage. And as the power increases, the concurrence decreases. And this is what we can tell from these plots. So next we have the concurrence for each channel pair as a function of the freezer temperature where the DSF is located. And we set the pump power to 12.5 dB because this data point just had the highest concurrence for all the channel pairs. So that's what we used over the ranging temperatures. The concurrence for all the channel pairs increased from about 0.74 to 0.79. Yeah, 0.79 as the temperature decreased from 20 to -86. And this is because of the reduced number of Raman scatter photons. So again, to characterize the type of photons produced in the system, in order to find optimal settings, we can use another method known as coincidence to accidental ratio. This is also known as CAR, so I'll refer to it as CAR. The CAR measurements don't determine the quantum state of the system, but it provides information about the relative number of entangled photons to noise photons output by the source. So to find CAR, we take the measured coincidences divided by the accidental coincidences of the two detectors. So an accidental coincidence is when two uncorrelated photons are simultaneously detected by the two detectors by chance. To measure the CAR value, the same experimental setup is used as we saw in previous slides, except we do not use the polarization analyzers. The fibers are therefore connected from the EPS directly to the detectors. And we're only collecting data for the maximum and minimum temperature. So that would be -86 and 20 degrees Celsius. Oh, it's also important to note that we did not take the measurements for channel 2933 because it had the lowest entanglement quality, as we've seen in the previous slides. It also had very high count rates in our preliminary experiments. So in order to not damage the equipment, we chose to exclude it from these measurements. The CAR power varied from 2800 to 3600, which is also lower than what we use for the tomography measurements, simply because we can perform the CAR measurements at a faster rate than we could have performed each tomography measurement. And for the CAR measurement, since we're connecting it directly to the detectors measure the number of singles counts for both detectors, the number of coincidences, and the accidental coincidences for a set number of gates that we manually input. So the CAR is shown for each channel pair as a function of attenuation at 20 and -86. For both temperatures, the CAR is maximized at around 14 dB, and it then decreases as the power is increased. This indicates the presence of noise photons due to self-phase modulation again. For both temperatures, channel 2834, which is the blue, achieved the highest CAR. So for 2834, it increased from 15.1 at 20 degrees Celsius to 23.4 at -86 degrees Celsius. And of course, this is due to the decreased rate of Raman scatter photons since we are cooling the DSF. So, So in summary, when we found that the Raman scattered photons and the self-phase modulation photons significantly reduced the source performance, and in order to reduce the amount of noise photons that are output by the source, we found that we need to decrease the temperature to the lowest possible setting to reduce the Raman scatter photons, and the pump power should be reduced to minimize the number of self-phase modulation photons to increase the entanglement quality. Okay, so at this point, we've looked at how to optimize the EPS settings and the effect that the noise photons have on the quality of the source. Now we're going to look at how we can approximate the number of photons generated by each nonlinear optical effect without additional coherence-based measurements to distinguish between the self-phase modulation photons, the Raman scatter photons, and then the single photons, which are generated via full-wave mixing. And as you can see here, I'm just giving you a little bit more background information. Some of the stuff I mentioned previously about how the EPS is easily integrated into fiber-based networks. And then in past experiments, people have used volt crystals to generate the entangled photons. So here, we're going to simultaneously measure the single counts and the coincidences of the two single photon detectors. And the measurements are then fit to a theoretical model of photon generation rates. And we're going to be able to determine the average number of photons produced by each nonlinear optical effect as a function of power in this case. And here is just an experimental setup diagram, similar to the one I've shown previously. And here's the experimental procedure used, also similar to what I previously described. But here we're fitting the measurements with the theoretical model. And the theoretical model of the photon generation rates. So the four-way mixing pair is characterized by measuring the singles and coincidences, which I mentioned before, at the varying pump power. And so we set the variable attenuator, then we measure the counts, change the attenuation, repeat, and simultaneously fit the measurements and then extract the data. So here we have the theory of detection. So basically we have the probabilities of a noise photon due to self-phase modulation, which models the behavior of the entangled photon. So I'm gonna go through this quickly. So PI, I can just tell you with all the variables. So PI, basically the probability that there's a single count in channel I. And then P12 is the probability that there is a coincidence detection. PRI, PSI is the probabilities of a photon generated via Raman scattering and self-phase modulation, respectively. And PFI is the probability of a detector clicking due to the presence of a four-wave mixing photon, and the other detector does not. And then PF9 is the probability that neither detector clicks due to the four-wave mixing photon. So the photon is detected. That's basically what the clicking symbolizes. The next formula is the single and coincidence count probabilities per detection gate. Here we have the individual probabilities of the detector clicking due to each type of photon, where, let's see. So mu represents the rate of the four-wave mixing photons. Ri represents the Raman scattering. Si is self-phase modulation. Ti is the transmission of the channel I, and Ni is the efficiency of the detector. So here we have figure A, which is the single and coincidence data fitted rates, and B is the plot of the coincidence data with fitted contributions from four-wave mixing in green, Raman scattering in purple, and then self-phase modulation in black. I would like to note that for figures A and B, we tested the Bayesian inference on experimental data, but it was trained on a neural network using simulated data in order to avoid the inclusion of like false correlations. The four-wave mixing photons are created in pairs. So the coincidence due to the four-wave mixing scale quadratically in power, but the Raman scattered and the self-phase modulation photons are created independently in each channel. So this means that the coincidence due to the self-phase modulation photons scale exponentially in power, but they can be approximated as a quadratic function, and the Raman photon scale linearly in power. Even though the four-wave mixing photons and self-phase modulation photons both scale quadratically in power, the generation of the self-phase modulation in one channel is independent of the other channel. This means that the probability of an accidental coincidence due to the self-phase modulation scales with the product of the self-phase modulation photon generation rate in each channel. And this differs from the probability of detecting a four-wave mixing photon pair. So in previous efforts to characterize the self-phase modulation photons, it relied heavily on like coherence-based measurements to distinguish between the self-phase modulation photons and the four-wave mixing photons. But with this fitting method, it distinguishes between the two photons with no additional measurements due to the different power dependencies of each type of photon. So in summary, throughout this presentation, we've looked at a new method to characterize the number of entangled photon pairs. We recognize that this last method does not need additional coherence-based measurements to distinguish between the self-phase modulation photons. Optimal temperature settings are required for the best entanglement quality when using the EPS. And we saw that lowering the DSF does in fact reduce the Raman scatter photons, and low pump power reduces the self-phase modulation photons to increase the entanglement quality as well. And any questions, I'll be happy to answer. Thank you.
Thank you, Atiyya, for your presentation. Please let us know if you have any questions. In the meanwhile, I got one question for you.
Okay.
What were some of the challenges that you encountered with these experiments, and how did you overcome them?
So one of the challenges that I face most often is being an experimentalist. Like sometimes you'll go into lab and things just won't work. Like simple as that, things won't work. But more specifically, the laser that we use for the EPS system, it stopped working, or some days it would work better than others. So my thing is just you had to adapt and kind of try to research and look at different experimental opportunities or different experiments that you could possibly do that relates back to your overall theme, so that like you're not wasting time, because in grad school we all know time is precious and we want to get results every day if we're lucky. So I would say that trying to deal with things like not cooperating and then keep pushing forward and kind of like entering into new like experiments, I guess.
Very good. Thank you. Are there any other questions for Atiyya? I think Emily had to drop off. If not, thank you very much for your participation. Just wanted to let you know that our next session is actually our sessions are the second Tuesdays of every other month. So our next session would fall under Tuesday, May the 14th. And thank you again for your participation. Thank you, Atiyya, for your presentation, and you all have a great day.